Okay, in this example, I want to show how you would go about doing a delta-delta CT type calculation. So this is an experiment where you performed reverse transcriptase quantitative polymerase chain reaction, RT-qPCR, to determine whether or not your new drug treatment has changed the expression of your target gene. In this case, we're calling the target gene LAMA1, and so we're saying, does drug number 1 or drug number 2 cause an increase and decrease in the transcript abundance and the mRNA abundance of this gene in these cells? And to do that, we use internal references, calibrators, known as reference transcripts, to provide a benchmark against which we can compare our LAMA1 mRNA values. And so usually you run at least 3, probably about 5 different reference transcripts, then calculate the geometric mean of their CT value. Now remember, the CT value is the point at which the fluorescence crosses above the background. So this is your CT value. For a more abundant transcript, that CT value comes up earlier, it crossed that threshold earlier, or for a less abundant transcript, the value is going to be later. So remember that a high number here equals less abundant transcript when you put it in. So the question we're really asking here is, what effect does the drug treatment have? Does it increase or decrease LAMA1? So let's put in some dummy numbers. Let's say in your untreated sample, you have a value of about 20, right? So that's the average of a whole bunch of biological repeats. You get a CT value of 20 for LAMA1. And then you have a reference transcript value of, let's say, 15. Okay, plausible. So you've obviously then take your drug treatment samples and have a look at them. Let's say for that, you have a value of 21. Now, obviously, you're looking at these two and you're thinking, okay, there's a 1 cycle difference. That would mean drug number 1 is coming up 1 cycle later, i.e. along this axis, which means that there's less in there. 1 cycle less means that there's actually 2-fold less, because it'd be 2 to the 1. But that's if we haven't taken into account any differences in the reference transcript. So let's say that that's 17 just for now. And let's put some numbers in for drug number 2 as well. While we're at it, let's go 19 and let's go 16. Okay, so these are, again, totally plausible numbers. And so to take into account, so basically what this shows, right, on the blue numbers, we can tell that we've got a difference in our internal calibrator. And we have to modify our upper values, our actual reference, our target gene, to reflect that difference in starting material. So all these comparisons are going to be against the untreated. So I'm going to use the untreated as my internal control here. So the delta CT relative to the untreated, we obviously have a 2 cycle difference here. 17 minus 15 is 2. This number's higher, so there's more more starting material in the untreated than there is in drug 1. So this is 2 cycles higher. So what that can mean is we've got we can put a minus 2 on here. So 15 minus 17 equals minus 2. And this is also 1 down, so this is minus 1. So this would be 15 minus 16 is minus 1. Now what we can do is use those numbers to change the top numbers. So effectively what that means is our actual values are 20, 19, 21 minus 2 is 19, and 18. So this is us now calibrated or adjusted our LAMA1 values to reflect the differences in the starting material. Hopefully that makes sense. And then this then gets known as the delta-delta CT. Oops, that auto-converted into a thing, but let's do that. So what we can see there is we now have minus 1 and minus 2. Now this number is less than that number, which means that this is more abundant. There's more abundant because it's come up a cycle earlier. So it's 2 to the power of minus 1, or 2 to the power of 1, i.e. there's twice as much of LAME1 in the sample from drug treatment number 1 than there is in the untreated. And similarly, this is 2 to the power of minus 2, which is 2 to the 2, which is 4. There's 4 times as much in drug treatment number 2.